Now, what about the integral part of thing? What if I want to find an antiderivative of pi to the x plus 2x to the pi, for instance? Let's start with pi to the x. We want an antiderivative. Pi is a constant and x is a variable. So we have the variable in the exponent and the base is constant. In other words, this is an exponential function, and we use a formula that we have right above the integral we're looking for, and we obtain pi to the x divided by natural log of pi, because we're integrating the exponential function of base pi. For the second term, we have 2x to the pi. Now this time the exponent pi is constant and x is a variable. So we have a power of the variable. We should use a power rule for antiderivatives. If I have x to the n, an antiderivative is x to the n plus 1 over n plus 1, provided of course that n is not negative 1. So we get 2 over pi plus 1 multiplied by x to the pi plus 1. This is of course up to a constant. Now to conclude on these natural exponentials before we turn to general logarithms, we're going to look at the graphs. We know what the graph of the natural exponential looks like, but what about different bases? Well, first observation, if a is greater than 1, that means ln of a is a positive number, and therefore when I differentiate a to the x, I get something positive. A to the x itself is always positive, but now I multiply it. When I differentiate, I multiply it by ln of a, which is also positive. So the function is going to be increasing and also concave up, because if I take the second derivative, I'm going to get a to the x natural log of a squared, which is again positive. So for instance, for 2 to the x, we get something like that. And to give you an idea of how the change in the base affects the shape of the graph, you see that if I take a base that is still greater than 1 but less than 2, like 3/2 for instance, the green graph, then this is going to positive infinity slower, still going through the point of coordinate 0, 1, like every exponential function, and it goes towards 0 when x goes to negative infinity, slower than 2 to the x. On the other hand, if I increase a base, I look at y equal 3 to the x, you see that it's going to positive infinity as x increases in a sharper manner, so it grows quicker. And on the side of negative x, when x goes towards negative infinity, it plunges towards y equals 0 quicker. Now let's look at an animation of what would happen if we start with a positive a and graph a to the x, and then let a decrease towards 0. So here we have a fairly large a, I think 3 point something, and you see that the graph is moving as a is decreasing. Now, a here is still greater than 1, but as a gets closer to 1, you see that the graph of the exponential is getting flatter and flatter until it is essentially the line y equal 1. And then when a is less than 1, well, we have a change of behavior. The function becomes decreasing, goes towards positive infinity when x goes to negative infinity, towards 0 when x goes to positive infinity. So that gives you an idea of the effect of changing a on the graph of the function. Right? At the end, we had a between 0 and 1. So more specifically, looking at that in a closer manner, if a is between 0 and 1, then of course the natural log is going to be negative. And that means the derivative is a positive quantity a to the x multiplied by ln of a, and that's going to be negative, meaning that the function is decreasing. The second derivative on the other hand is a to the x multiplied by ln of a squared, so that's going to be positive, and therefore the graph of the function is going to be concave up. That corresponds to what we've seen on the animation. Now looking at the difference between the case a greater than 1 or a less than 1, you see that if you're looking at the red graph, 1/2 to the x, so the case where a is between 0 and 1, we can write that 2 to the negative 1 to the x, in other words 2 to the negative x. In other words, this corresponds to plugging negative x instead of x in the function y equal to 2 to the x. So that means the red graph is really just the image of the black graph, y equal to 2 to the x, by reflection about the y-axis. So, in other words, in general, if a is between 0 and 1, then 1 over a is greater than 1, so 1 over a corresponds to one of the graph we discussed in the first case, and then we just take the reflection about the y-axis of that 1 over a to the x. So in particular, we get this kind of picture in terms of the effect of changing values of the base. So here, for instance, the larger a is 2/3, so you get this green graph, 2/3 to the x, and you see that it goes to positive infinity as x goes to negative infinity slower than 1/2 to the x when we decrease the base, when the base gets closer to 0. And as we go closer to 0, going down to 1/3, then the growth towards infinity as x goes to negative infinity is quicker, and similarly it goes to 0 quicker when x goes to positive infinity. Now turn to the next video to discuss general logarithm functions.